Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing the multiplexers and the demultiplexers. In the previous lecture, we discussed a few combinational circuits, which were the multipliers and the comparators. In the current lecture, we will be discussing few more combinational circuits, which are known as the multiplexers and the demultiplexers. There are few combinational circuits which are very commonly used in different digital systems. These are known as the multiplexers, demultiplexers, encoders, and decoders. For the course of next two lectures, we will be discussing these basic combinational circuits because these are widely used and a very integral part of any combinational circuit. The first that we are discussing here is the multiplexer. Multiplexer is generally represented by this symbol. Multiplexer is defined as a system which extracts or which connects a given input to any given output. Generally, we say it that it is a many to one form representation. We say it as many to one, which means that it could have many outputs but it has only one output. Generally, we represent it as in this way. Suppose we have a 2-bit input I0 and I1, and then we have a one output Y. So basically, we use a select line, which is represented here by S, to connect any of these two input signals to an output signal. So for this purpose, the multiplexer could also be defined as that it selects binary information from one of many input lines and direct it to a single output line. There could be 2n input lines, and for any 2n input lines, there should be a n selection line, and there would be only one output line. Generally, we calculate this thing as a similar manner as we used to calculate the number of bits required to represent any given decimal number, just like that. Because if you take the log 2 of the number of inputs, then that would give you the width of the selection line. Suppose for this example, we have a 2-input system. This is basically, you can also represent it as 2 to 1 line mux, or you can just represent it as 2 cross 1 mux. So in this case, there are 2 inputs and 1 output of the system. If you take the log of this, log 2 of this, then that would give you the width of the selection line that you have to run. So in this case, the selection line would be equal to 1 bit. So now we will check that how this mux or the multiplexer work. First, we design a truth table for that. Here we have a selection line which is represented as S, it is 1-bit line, and this is representing the Y is representing the output of the system. We have two inputs here, one is the I0 and the other one is the I1. What mux do is at any given time, depending upon the value of S, it selects one of the input and connect it to the output. Means that when say S value is equal to 0, when S is equal to 0, then the output is connected to Y0 or the first input. When S is equal to 1, then output is connected to I1, which is the second input. So in this way, for a given value of S, we can select different inputs of a given system, and then we can connect these inputs to the output. So for when S is equal to 0, we can develop a circuit for that, and similarly for when S is equal to 1, we can also develop a circuit for that. It is quite simple circuit. You can see that we have represented them by two AND gates. This is the selection line here. When the selection line value is 0, say when S is equal to 0, then in that case this value would be equal to 1, and we would have 1 here. In this case, we would have 0 here. Because of having 0 here, this AND gate will not correspond to any changes in this I1. But when this value is 1, then what actually happens is that whatever the value of I0 here will appear in this part too. And similarly, if we OR that, because its result will always be equal to 0 because of this 0. So we will get I0 at the output. So in this way, when the selection line value is equal to s is equal to 0, then we will be getting I0 at the output. So it means that y is connected to the first input of the system. While say if we give it to the value of s1, then we would have a 0 here after the inverter. 0 would go here and make it 0 here. So because when this term is 0 here, that would make its output equal to 0 at that time. But because when it's equal to 1, we will now have a 1 here instead of the 0, and this I1 will be transferred here. And similarly, this would become 0 here, and this would become I1 here. So when value of s is equal to, or selection line is equal to 1, then we would get the second input to the output. So in this way, a basic multiplexer works. It selects any of the given input depending upon the value of the selection line that you have chosen. So in this way it connects, it's just as you can say a connector which is connecting this output to either this one, or it is connecting it to this one depending upon the value of s. And we can represent this whole circuit in a form of a simple Boolean expression in this way, that I naught into s complement or I1 into s should be equal to y. So in this way, at any given value of s, we would have y equal to I0 or y equal to I1. Now we will be expanding the same concept to more number of inputs. Now we have increased the number of inputs from 2 to 4. This is now known as the 4 to 1 line mux. In this system, we have 4 inputs, 0, 1, 2, 3, and we have only one output. And now because there are 4 inputs, if we take the log 2 of 4, then that would give us 2. So it means we have to select 2 selection line S0 and S0, we can represent by them. So this is represented by S0 and this is represented by S1. Because S0 and S0 are 2 bits, so we can form 4 different combinations of this. So if we form a truth table, then from the truth table we can see that there are 4 different combinations, and for the each combination you can see that the one output is activated only. When the combination, when S0 and S1 both are equal to 0, then Y is equal to I0, the first one. When it is equal to S1 is equal to 0 and S0 equal to 1, that's it is representing the second combination. Then in this case the 1 is connected to the output. Similarly, when it's 1 0, then the second input is connected to the third input I2 is connected to the output, and when both of them are 1, then the last input is connected to the output. So from the same mechanism which we discussed in the last slide, we design a mux. This mux is known as a 4 to 1 line multiplexer. We can just represent it as 4 cross 1 mux. It depends upon the selection line or the values of the selection line that how its output would be generated. Its circuit is almost the same which we discussed in the last slide. We have just addition of 2 more inputs here, and we have added one more selection line. So in this case we have added a single more selection line. We would take 4 combinations. For that 4 combination, what we need to do is we need to have both the complemented and the uncomplemented value of the S0 and the S1 terms. So we have taken the 2 inverters here which are representing the complement terms here. The rest are representing the normal S1 and the S0 term. We have 4 AND gates here that are representing the output that would be used here for the next gate. At any given time, only one of them would be generating a value, while all the rest would be equal to 0. Suppose we select S1 is equal to 1 and S0 equal to 0. Say this is equal to, we take any one value or any one combination from here. We have 1 here, S1 is equal to 1 and S0 is equal to 0. In this case, what would happen is that if you see this combinations, then this 0 is first connected to this one, so we will get a 0 here. Then this 0 is also connected to this one here, so we would also get a 0 here. This one is connected here, so we will get a 0 here, which is then connected to this one and this one. And as you know that if any given input or one input of the AND gate is equal to 0, then its output would also be equal to a 0. So in this case we are only left with this AND gate in which both of the values are equal to 1, because from here you can see that what we will have is that we will be connected S0 here 0. This would give us a 1 here, and this one is also connected here, and the other thing that is connected here is the I2 here. So in this case the output of this AND gate would be equal to I2, and similarly when all other values are equal to 0 0 0, we would have only I2, and that would be this. So y is equal to I2. So in this way they are 4 into 1 multiplexer works, that at any given combination of the selection line we can select one input and join it to the output. So this is the case. We have discussed this case now. Similarly, for all other entities we can also design a similar mechanism. The circuits remain the same. Now we will be seeing some other utility of these multiplexers. These multiplexers could also be used in a slightly different scenario. First, what we do is we added an other input to the system. Instead of the selection line, we have added another input which is known as the enable input. In the enable input, the purpose of the enable input is to activate the whole system. Generally, this enable input is present in most of the common ICs that we use to design any given digital system. Its purpose is to control the whole mechanism of the system. If you look at this truth table, what this circuit do is this for this circuit we have an active low enable. For active low enables mean we can also represent this E as sometimes as E complement, or we have to look at the truth table to identify whether all the values whether it is active low or active high. When our circuit operates correctly on E is equal to 0, then that means it is representing an active low circuit. It could be represented as E bar, E dash, or simply E, but we then have to check the truth table for it. For example, in this case we are representing it just as a normal enable thing, but we can check from the truth table that what its purpose is. Whenever this value of the circuit and value of this enable bit is equal to 0, only then this circuit will perform its operation. Whenever this value is its value is equal to 1, then in that case all the output would be equal to 0. So to operate this system we have added an input which is known as the enable input. We could add it to any given circuit. What is the function of enable is that we just add an extra input to all the AND gates that are involved in the multiplexer circuit, and we connect them to the enable input. So if enable is say 1 required, then whenever this value is equal to enable value is equal to 1, only then we would get any output. In this case we are using the active low enable. So in this case whenever the enable value is equal to 0, we would get inverted output here as equal to 1. Then only in that case we would be getting the correct output. So for this circuit we have an active low enable. So for the circuit to work properly, its value should be equal to 0. And now we will look at what is this circuit is doing or performing. This circuit is, you can say, call a quadruple 2 to 1 line multiplexer. It is acting like a 2 to 1 line multiplexer, but instead of the 2 inputs we have 2 quadruple inputs. It means that we have 2 inputs that are represented by two 4-bit numbers. First number is represented here as A naught to A3, and the second number is represented as B naught to B3. What we do here is that we use a single select line, because for a general 2 to 1 line mixer we need only a single bit select line. So we have chosen a select line of 1 bit, which is represented here as this one. And for this select line, if we choose the value of select line equal to 0, then in that case we will be selecting these four. It's the A0, A1, A2 and A3 to the output. So in this example of the multiplexer, we are treating each single bit or single line as a 4-bit number. Because the two inputs that are represented here are also represented in 4-bit form, A0 to A3 and B0 to B3, and similarly the output is also represented in a form of 4-bit number Y0 to Y3. So what we do here is that depending upon the value of the selection line, we select any one of them. If we select S is equal to 0, then in that case all these four numbers A0 to A4, which are representing the A or the first quadruple, will be connected to the output Y0 to Y3, while if we select S is equal to 1, then in that case all the 4 bits of number B from B0 to B3 will be connected to the output Y0 to Y3. So in this way we have extended the concept of the multiplexer. Instead of just dealing with the 1 bit or 2 bit input, we are now dealing here with a quadruple input. Means we have two numbers of 4-bit and we are connecting these two numbers of 4 bits to the 4-bit output number. The overall mechanisms of the system remains the same. You can easily see that the architecture of this multiplexer is very similar to the one which we discussed in the last few slides. We have only added the additional enable bit here. Because enable bit only enables us that when we will get the output of the given circuit. If you choose say S is equal to 0, if we select just S is equal to 0, put S is equal to 0 here, and then after the first inverter we will get 1 here, and after the second inverter we will get 0 here. So when we have this input here, you can see that this input is connected to this one will go to here, 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 while 0 will be connecting to here, here, here. Because all these have zeros in the input, so these AND gates will produce 0 at the output. While if the enable, we are considering here that enable is also equal to 0 here. If we are set enable equal to 0 here, then that would also correspond to say 1 here, 1 here, 1 here and 1 here. So the remaining inputs of all the AND gates are the A0, A1, A2 and A3. So whenever we select this combination that enable is equal to 0 and the select line value is equal to 0, then in that case we will be connecting this A0 to the Y0, A1 to the Y1, A2 to the Y2 and A3 to the Y3. Similarly, when we would select S is equal to 1, then in that case this combination of 4 bits will be connected to the output. So this is a common implementation or use of a multiplexer in terms of having a number which is more than of 1 bit. Now we would see that how we can use this multiplexer to represent any given Boolean function. Because so far what we have seen is that the multiplexer is used to select any given input. Now we would see that how we can use this mechanism to represent any given Boolean expression. We have taken the example of an exclusive OR gate. Exclusive OR gate is represented in form of the minterms like this one. So if we just connect the two selection lines here, if we connect the two selection line of a 4x1 multiplexer to a simple gate, then that would produce a system that is that performs the functionality of generating the minterms. So what we need to do is we need to design a mechanism that in which we have the main terms, and now we need to connect these main terms or relate these main terms to the input of the multiplexer so that we can perform any given function. Suppose what we do here is that these A and B represent the system's input. Both of them are 1 bit, so will form the 4 combinations here. And the output, we know that for an exclusive OR gate is that for 0 0 we have 0, for 0 1 and 1 0 we have 1 1, and when both of them are 1 we would also get a 0 here. Now we have to relate this thing to the multiplexer concept. So what we do is that we connect the both of these inputs to the selection line of a 4 cross 1 multiplexer. So we connect this A to the S0 and B to the S1 bit. So this would what we are doing here is that we are generating these 4 combinations of the main term here. So if you consider a 4 cross multiplexer like this one, in this case what we are doing here is that for value of S0 and S1 both equal to 0 or the first combination, we are basically connecting the input I0 to the output. When we are having value 0 1, then we are connecting the output equal to I1. When we have 1 0, we are connecting the output Y to the input I2. When both of them are equal to 1, then in that case the output is connected to the I3 term. So we are connecting all the input terms here. So what does this table mean? This table means that if we are considering that S0 and S0 are basically the two inputs of this system, which are representing as A and B in the table or the exclusive OR system, then in that case I0 should be equal to 0 from the table's first entry, I1 should be equal to 1, I2 should be equal to 1, and I3 should be equal to 0. So what we do here is that we connect the two inputs of the system to the two selection lines, which are represented as S0 and S1. So we connect A with S0 and B with S1. And by seeing this table, which is derived from this main truth table, we can see that the first value is 0, means that I0 is equal to 0 here. Then I1 is equal to 1 here, I2 is equal to 1 here, and I3 is equal to 0. And this would equal to function. And now how this whole system works, when we have a selection line, say we take the first entry when both A and B are equal to 0. When both of them are equal to 0, we will be connecting the first input of the system I0 to the output of the system, which is represented by F here. So when both of them are 0, this 0 would be connected to output, and that case we are requiring that 0 should be for the exclusive OR. So if we fix it value to 0, then we will get 0 at the output. Similarly, if we select this line as 0 1, then in this case we are connecting the second input of the multiplexer to the output of the system. So I1 would be connected to F here, whose value should be 1 according to this table. So we connect a 1 here to the second input. Similarly, for the third one, 1 0 case, in that case this input would be connected to the output. So it for the exclusive OR it should be equal to 1. So that is connected to 1 here. And for the last combination 1 1, we should have a value of 0. So in this way we are connecting a 0 here. And so when we would have a 1 1 selection line here, this output or input I3 would be connected to the output, so we would get a 0 at the output. So the main thing is that how we have to set the values of this thing. We can easily see these things from the truth table and adjust these values accordingly. Now we will be using another form of the implementation, or you can say a more efficient way to implement any given Boolean function using the multiplexer. We have designed a separate procedure in that. What we do here is that for the n selection line, we select an n selection line, and one selection line we take it from the input. We design a separate procedure for this thing, that we first have to use the leftmost variable, which has the input lines. we will assign the remaining n minus 1 variables to the selection line, which should be corresponding to the sequence, and then we should list all the min terms. We will try to explain this concept through an now, in this example, we will be seeing another type of implementation for the multiplexer to represent any given Boolean expression or Boolean function. Suppose we have a Boolean function which is represented by these min terms 1, 2, 6, and 7. If we see the last example, then we can see that we have to use a multiplexer in which we have a 3-bit selection line. But we can also represent the same function using an efficient implementation using only a 4 cross 1 multiplexer, because in a 4 cross 1 multiplexer we only have 2 bits selection line. So what we do here is that we first represent the two inputs here as the two selection lines. S0 and S1 are representing the two selection line. The next input is connected to the first input of the main system or the multiplexer. So we have connected the next input, which is Z here, as the first input to the system. Now we will see that how we can use this multiplexer to represent this Boolean function. For the timing, just ignore these expression and just focus on these input combination. We can see that there are 2 bits of selection line. For the multiplexer, we would have 4 different combinations. So we have can represent all the 4 combinations here, as this is the representing the first combination when both of them are 0. This is part is representing the second. This is representing the third, and this is representing the fourth combination of the input, because for the multiplexer we have only 2 selection lines that are directly connected to the S0 and X1, which are the X is connected to S1 while Y is connected to the S0. And then we have the output, third output input, which is Z. We have connected this to the first input of the multiplexer. First, what we need to do is we need to have a look at this. When we have both of them equal to 0, it means that when we have the first combination, that when X and Y are both equal to 0, then in that case, what we require to have is that if Z is also equal to 0 for that case, then our function should also be equal to 0, means F should be equal to 0 in that case. And if we have both inputs equal to 0 and we have 1 at Z, then in that case the output should also be equal to 1. F should also be equal to 1. So it means that for a combination of 2 selection line of 0, 0, we could have 2 more combination added to it depending upon the how we choose the value of Z. So we have chosen value of Z could be either 0 or 1. So these 2 combinations are now extended. One combination is extended to 2 different combinations depending upon the value of Z. One would become 0, 0, 0 and other would become 0, 0, 1. So in this case, if you see this table or the truth table for this min terms, we can see that the value for the first min term should be equal to 0 while the next should be equal to 1. So if you see that this thing here for the first combination is equal to this one here. So we can say that when we have both S0 and S2 equal to 0, 0, then in that case we would have F is equal to Z for this circuit. So in this case we would have the same function output would be equal to the input that is connected to the first input, which is the Z. So whatever we have a value of Z here would be connected to the output F. So in this way, we would be representing these first 2 combinations of this table. And then for the next 2 combination, we move on for the next combination. For the XY only, we would have 0, 1 combination here. For the 0, 1 combination here, we can have value of Z either equal to 0 or 1, which would extend it again to 2 different min terms. One would become 0, 1, 0 and the second would become 0, 1, 1. So in this case, what we required is that because our min term 2 is equal to 1 and the min term 3 is equal to 0, so we should have a 1 here and 0 here. So we have 0, 1 here and 1, 0 here. So if you just relate these 2 things, you can see that these are the form the complement of the Z. So in this case, what would happen is that our mux would be connected to this second input of our system, and which is equal to the Z complement of the input. Z is our third input, so it is equal to the Z complement. So in this way we will be connecting the second input here. So whenever we choose 0 1 here, we would be basically selecting this input here, and depending upon the value of Z, we could have a function value of either equal to 1 or equal to 0, which is actually the opposite or the complement of the value of Z. So we could just connect it here as the Z complement here. Similarly, for the third case we have here is that x and y are equal to 1 0. In this case, you see that the next combination, the 4 and the fifth min term here, both are not representing, or both are representing the value of 0 here. So for both of these terms, we would have a 0 at the output. So for these two combination of 1 0 0 and 1 0 1, we just connect them using a simple 0 to the input 3. So this is the third input here. So now when we would have 1 0 here, then this would be connected to this I2 term here, and which is connected to 0 because it is corresponding to the function. Similarly, when we have the last two values of 6 and 7, min term 6 and 7, then for these min term 6 and 7, we have both values equal to 1. In that case, what we can do is that for any combination of S0 and S1 equal to 1 1, we can just connect it to the hardwired 1. So in this case, we have connected it to the 1. So now this multiplexer system will behave as the logic implementer of this boolean function. We have to just connect the values x, y and z here to the input. X would be connected to S1, while y is connected to S0, and z is connected to the first input of the mux. Now when we use these combinations, we will be connecting either to this term, this thing and this thing. So in this way, we have represented a 3 input boolean function in a form of or using a multiplexer. Now we will be discussing the same kind of example, but this time we are using a 4 input system, and that 4 input system is representing here as in a form of an 8 cross 1 multiplexer, which will be using to represent this system in a form of a boolean function. So what we need to do is we need to first connect all the terms here. S0, S1 and S2 are connected here. So the first three of the terms are connected here. The S0 is corresponding to the C here, S1 is corresponding to B, and S2 is corresponding to A here. While the fourth term, the D value, is connected to the first input of the system. Now we will see that how this whole system would work, because overall we have for this system we have three inputs or 3-bit selection line for the 8 cross 1 mux, and depending upon the values of these, we could have two different values of D. Either it could be 0 or either it could be 1. So for each of the combination that are formed here for the bits, three combinations that are formed using the S1, S2 and S3, we can add the other value of the D as 0 or 1. So first, if you just consider A, B and C here, which are representing the selection line S0, S1 and S2 here. So, and for any given combination of these one, we would have either D equal to 0 or D would be equal to 1. So in this case, we would, if we look at this, we have function value of min term equal to 0 is equal to 0. So the first min term value is equal to 0, while the min term M1 is equal to 1 here. So if you see that this combination is again equal to this function output, so we can represent here as F is equal to D. So whenever we have all the selection line equal to 0, then this function output will be F would be connected to basically the first input line, and that input line will be equal to the D input. So whatever the value of D, it would be connected to the output. Now we see the next combination. Now we are involving the min term 2 and min term 3. For min term 2 we have a 0 here, and min term 3 we have a 1 here. And again you can see that for this combination again we would follow that F is equal to D. So for this first min term and the second min term, we would have the same thing. So it is also connected to the same line as this one. Then we see the next one. For the 0 1 0 combination, we have D either equal to 0 or 1. But for this one we have a boolean function which is opposite of it or the complement of it, so we can use the it as f is equal to d complement. Then we see that there are four minterms after that, minterm 5, 6, 7, 8, 9, 10. These values are equal to 0. So for all these terms that are equal to 0 here, regardless of what the value of d is, we just connect them with the 0. So we have connected the 3 and 4 with the equal to 0. So for the next one, what we're going to do is we see that if you use the next combination, then in this case again we can see that both of them are equal, so f should be equal to d, so d is also connected to fifth here. And for the last two terms, whatever we choose the input combination, we have the output always equal to 1, so we can just directly connect it to the 1. So in this way we can represent any given boolean function using the multiplexer. We have seen two different ways of representing it. The second method which we have discussed this in this slide and the previous slide is the more efficient implementation of it. Because in this we are using the multiplexer which have a reduced number of selection lines as the number of the input per step we can implement or any given boolean function with it. The only thing that differs is how we use this circuitry, that how we can use this, because value should be either equal to 1 or 0. So depending upon how we have our minterms values are, we can easily design a mechanism in which we can connect it up to either 1 or 0 or to the input d. So in this way these things are generally different for any given boolean function. The rest of the part remains the same. And now we will be discussing an other important concept which is known as the demux or the de-multiplexer. It is basically called the data distributor, and it is exactly the opposite of what we have discussed in the multiplexer. It is defined as one-to-many system, because if you see this as a symbolic representation or block diagram representation, it has one input and it is connected to multiple outputs. We can say that it has one input line and we have about 2 to the power n output lines, and for the 2 to power n output line we would be requiring n selection lines. So this is representing the selection line here, this is the input, and these are the two outputs here. If we just draw a simple circuit of a 1 to 2 line demux, then that is represented in a similar way, that if value of s is equal to 0, then we would be having the input would be connected to the first output. When we would having s is equal to 1, then in that case the second output is basically connected to the input. We can easily draw its circuit is very similar to the one we discussed in the multiplexer. We have a selection line here, we would have a 1 and 0 combination using this inverter here. At any given time only one of the AND gate would be producing the output. So at any given combination of s, we would be connecting the input to either y0, or we would be connecting input to y1. So we can represent this in a form of expression like this one. Extending the idea that we discussed in the last slide to 1 to 4 line demux. For the 1 to 4 line demux, we would have a one input here, and we will be having a 4 different outputs here. Because we are having 4 different outputs here, we can choose the selection line, or the width of selection lines at log 2 to the power 4, which would be giving us 2 bits. So we would have a 2-bit selection line here. For the 2-bit selection line, you can easily say that we have a 4 combination. For each of these 4 combination, only one output would be connected to the input. Say when both of them are equal to 0, then in that case we are connecting the output y0 to the input I. When we have input combination selection line combination equal to 0 1, then in that case we are basically connecting y1 to the input. And similarly, when we have 1 0 combination at the selection line, then we are connecting y2 to the input. And when we have 1 1 in the selection line, then we are basically connecting the y3 output to the input. So we can represent all these expression in terms of the Boolean expression as in this way, and we can easily draw its circuits. It's very simple as this way. We are just extending the mechanism we discussed in the last slide to a 1 into 4 demultiplexer here. Similarly, at any given time, only one of the AND gate would be producing an output which would be actually equal to the I, or the input of the system. Kindly do read these pages for better understanding. Thank you.